Tonight, the fastest object humanity has ever launched into interstellar space is travelling at about 61,000 kilometres per hour. It has been travelling since 1977. It crossed into interstellar space over a decade ago. It is, by any everyday measure, impossibly far from Earth. And it has covered less than 1/20th of 1% of the distance to the nearest star. The nearest star, not a distant star, not a star on the other side of the galaxy. The closest one. Our immediate neighbour, astronomically speaking, 4,024 light-years away. At Voyager's current speed, the trip takes approximately 73,000 years. Tonight, you are going to understand why going faster does not actually solve this problem. Why nuclear propulsion moves the wall but does not remove it. Why the interstellar medium becomes lethal at the speeds required to make the trip in a human lifetime. Why the body cannot survive the transit, and why the one proposal that might actually work only works for something the size of a postage stamp. This is not a script about how far we still have to go. It is a script about why the gap between us and our nearest star may be one of the most permanent facts about the universe we live in. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. There is an object leaving our solar system right now. It has been travelling since 1977. 47 years of continuous motion, covering ground every second of every day, moving away from Earth at roughly 17 kilometres per second. It has long since passed the outer planets. It has crossed the heliopause, the boundary where the sun's solar wind gives way to the interstellar medium, the thin, cold space between stars. It is, by any measure of human achievement, one of the most extraordinary things we have ever done. Voyager 1 is approximately 23 billion kilometres from Earth. That number is so large it is almost impossible to feel. So here is a comparison. The Moon is about 384,000 kilometres away. Voyager has travelled a distance roughly 60,000 times farther than the Moon. If you drove a car at highway speed without stopping, you would reach the Moon in about 5 months. To reach Voyager's current position, that same drive would take roughly 30,000 years. 30,000 years of driving. And Voyager has not even begun to cross the distance to the nearest star. Proxima Centauri is approximately 40 trillion kilometres away. 40 followed by 12 zeros. At Voyager's current speed, the trip would take somewhere around 73,000 years. Not decades, not centuries. 73,000 years, which is longer than the entire span of recorded human civilization, which is longer than the time since modern humans first left Africa, which is longer than any continuous human institution, tradition, or technology has ever survived. This is the number at the centre of everything this script covers. Not because it is the largest number in astronomy, it is nowhere close to that, but because it sits at a specific intersection of size and human timescale that makes it uniquely devastating for the idea of interstellar travel. It is not so large that it becomes abstract. It is just large enough to remain specific. Large enough to mean something when you press it against any proposed solution. Start with the comparisons that most people use to make this feel manageable. Astronomers call Proxima Centauri our nearest neighbour. The word neighbour implies proximity. It implies a walkable distance, or at worst a short drive. In astronomical terms, Proxima is indeed close. The Milky Way is roughly 100,000 light-years across. The nearest large galaxy, Andromeda, is about 2.5 million light-years away. On that scale, 4024 light-years is practically next door. But you are not an astronomer sitting at a desk drawing maps. You are a biological creature who ages at a fixed rate, moves at biological speeds, and lives inside a body that requires food, air, water, and a gravity field it was built for. The word neighbour means something different to you than it does to a coordinate system. Here is a comparison that gets closer to the truth. Shrink the solar system down. Make the sun the size of a grapefruit. On that scale, Earth is a small bead about 15 meters away. Neptune, the outermost major planet, is about 450 meters from the grapefruit sun. Voyager is currently a little over a kilometre out. Still visible. Still within the neighbourhood in some sense. On that same scale, Proxima Centauri is in another city. Not a distant suburb. A different city, roughly 4,000 kilometres away, depending on the reduction factor. The scale model of the solar system fits inside a large building. The scale model that includes Proxima Centauri spans a continent. There is no scale at which these two things, the solar system and the nearest star, belong to the same neighbourhood. The word nearest is doing a kind of linguistic violence to the actual situation. Now add motion. Humanity has been launching spacecraft for about 65 years. In that time, we have sent objects to the Moon, to Mars, to Jupiter, to the edge of the solar system. We have landed on comets. We have flown past Pluto. Every one of these missions operated within the scale model of the solar system, the building, not the continent. Every propulsion system ever designed, from the Saturn V to the ion drives on current spacecraft, was calibrated for that building. Proxima Centauri is not in the building. Voyager is proof of both things simultaneously. It is proof of what we can achieve, a spacecraft launched nearly half a century ago, still functional, still transmitting, crossing into territory no human-made object had ever reached. And it is proof of what that achievement means at interstellar scale, almost nothing. After 47 years of travel, it has covered a fraction of the distance that rounds, on the scale of the problem, to zero. The nearest star is not far away in the way that a distant mountain is far away, where the difficulty is the climb but the destination is at least reachable by walking. It is far away in a way that introduces a different category of problem entirely. A category where every solution humans have ever developed for moving through space is the wrong tool for the wrong distance, in the way that a canoe is the wrong vessel for crossing an ocean. The unit used to measure that distance deserves attention because it contains the problem. A light year is not a unit of time, it is a unit of distance. The distance that light, travelling at 300,000 kilometres per second, covers in 1 year. That works out to roughly 9.46 trillion kilometres. It is used by astronomers because it is a convenient scale for the distances involved. In the same way that you might measure road distances in kilometres rather than centimetres, astronomers measure interstellar distances in light years rather than kilometres. But there is a consequence embedded in the unit that the name makes unavoidable. The light you see when you look at a star left that star some number of years ago. When you look at the sun, you are seeing it as it was 8 minutes ago. When you look at Proxima Centauri, you are seeing it as it was 4.24 years ago. The image of Proxima in any telescope is not current. It is a 4.24-year-old photograph. This is not the important consequence. The important consequence is what it means for travel. If you sent a signal to Proxima Centauri right now, the signal would arrive in 4.24 years. A reply would arrive 4.24 years after that. You would wait 8.48 years for the round trip of a single exchange. If you sent a spacecraft at the speed of Voyager, the spacecraft would arrive in 73,000 years. Any signal from it would take 4.24 years to return to Earth after arrival. You would be waiting for a reply that no one alive when it launched would ever receive. The light year is a unit that measures distance in the currency of time, and time for biological creatures with finite lifespans is the most precious and least expandable resource in the calculation. 4,024 light years is 4.24 years of light speed travel. It is also 73,000 years of current spacecraft travel. The difference between those two numbers, the ratio of 73,000 to 4.24, is the size of the gap between where humanity currently is and where it needs to be to make the nearest star reachable in any meaningful sense. That ratio is 17,200. Humanity needs to travel 17,200 times faster than Voyager to reach Proxima in the time it takes light to make the trip. And light is the speed limit. Nothing with mass can reach it. The fastest anything can go is slightly less than light speed, and achieving even a fraction of it requires energies that the civilization currently cannot produce. Parker Solar Probe, currently the fastest human-made object ever built, reached a peak speed during its close solar approaches of approximately 163 kilometers per second. That is about 10 times faster than Voyager. It is also about 0.05% of the speed of light. At Parker Solar Probe's peak speed, the trip to Proxima would take approximately 7,800 years. A significant improvement over 73,000 years. Still 7,800 years. The fastest speed ever achieved by a human-made object, the current record, expressed as a fraction of what would be needed to make the trip in a human lifetime, is less than 1% of the way there. This is not meant as a criticism of the engineering that produced Parker Solar Probe. That spacecraft is an achievement of extraordinary precision and design. It is meant as a calibration of where the baseline is. The fastest humanity has ever managed to move anything is 7,800-year trip to the nearest star. The target is somewhere around a 20-year trip. The gap between those is not a gap that incremental improvement fills. It requires a different kind of propulsion entirely, operating at a different energy scale entirely, producing different speeds by orders of magnitude. And the ocean is not the hardest part. The obvious answer to the distance problem is speed. If Voyager is too slow, build something faster. Go faster, close the gap. This is the intuition that has driven nearly every serious proposal for interstellar travel since the 1950s, and it is not wrong as far as it goes. Speed does matter. The faster the spacecraft, the shorter the trip. The logic is clean and obvious and correct. The problem is what speed costs. To understand that, you need to understand how rockets work, not the engineering details. The mathematical principle that sits underneath all of them, from the Saturn V to the most advanced ion drive, from chemical propellant to theoretical nuclear systems. There is one equation that governs them all, written by a Russian schoolteacher named Konstantin Tsiolkovsky in 1903, and it is one of the most merciless equations in all of applied physics. The Tsiolkovsky rocket equation says this: the change in velocity a rocket can achieve depends on two things: the speed at which gas exits the engine, called the exhaust velocity, and the ratio between the rocket's starting mass and its ending mass. That ratio is the key. The starting mass includes all the fuel. The ending mass is what is left after the fuel is burned. Here is where the cruelty begins. To go faster, you need more fuel, but more fuel means more mass at the start. More mass at the start means you need even more fuel to push that mass. which means more starting mass, which means more fuel again. The relationship is not linear. It does not grow with addition, it grows with multiplication, exponentially, compounding against you with every incremental increase in desired speed. Think of it this way. Imagine you are trying to carry enough water to cross a desert. The further you need to go, the more water you need to carry. But carrying more water makes you heavier. Being heavier means you burn more energy walking. Burning more energy means you need more water, which makes you heavier, which means you need more water still. There is a point where the math collapses, where the required amount of water exceeds what a human body can carry, and the desert becomes uncrossable not because the water does not exist, but because the equation prevents you from carrying enough of it. Rockets in space face the same trap. With chemical propellant, the exhaust velocity has a physical ceiling determined by the chemistry of the reaction. No matter how clever the engineering, no chemical reaction releases more energy per kilogram than the best available fuels already do. That ceiling is fixed by atomic physics, not by engineering effort. At that ceiling, here is what the rocket equation says about interstellar travel. To accelerate a payload of 1,000 kilograms to 1% of the speed of light using chemical propellant, the required fuel mass at launch is not 10 times larger than the payload. Not 100 times. Not 1,000. The number runs into the many millions of tons of fuel for every kilogram of payload, and it keeps climbing as the target speed rises. To reach even 1% of light speed, the required fuel mass under chemical propulsion exceeds the mass of everything humanity has ever built, combined many times over. The rocket equation does not care about engineering ingenuity. It does not reward clever design or larger factories or more funding. The exhaust velocity of the best chemical reaction possible is fixed. The required fuel ratio for interstellar speeds is fixed. The two numbers multiply together into a wall that no amount of determination can move. Chemical rockets were the right tool for reaching the moon. They were the right tool for reaching Mars. They are the right tool for everything humanity has launched into space for 65 years. For interstellar travel, they are a canoe being asked to cross an ocean. Not because canoes are poorly made. Because the ocean is an ocean. The rocket equation does not close with better chemistry. Something fundamentally different is required. It is worth sitting with this for a moment, because the intuition that more engineering effort solves engineering problems is deeply ingrained and almost always correct. In most domains of human endeavour, if a current technology is insufficient, you build a better version. You improve the efficiency. You use better materials. You increase the power output. The gap closes incrementally until it closes completely. The rocket equation does not respond to this. It is not a technology problem. It is a mathematical relationship between desired velocity, exhaust speed, and mass ratio. The desired velocity for interstellar travel is fixed by the distance. The maximum exhaust speed of chemical reactions is fixed by atomic physics. The mass ratio required by those two fixed numbers is a consequence, not a design choice. You cannot engineer your way around a mathematical consequence. This is what makes the chemical propulsion wall different from, say, the early challenge of building better telescopes, or the challenge of miniaturizing electronics, or the challenge of improving solar panel efficiency. All of those problems respond to engineering effort. The rocket equation at interstellar velocities does not. It simply states, with mathematical precision, that the tool is insufficient for the task by many orders of magnitude, and that improving the tool incrementally cannot change that assessment. The wall is not made of technical difficulty, it is made of mathematics, and the difference matters enormously for understanding why the history of proposed solutions to this problem moves immediately to entirely different physical regimes, not to better versions of the same regime. There is one more consequence of the rocket equation that deserves attention before leaving it. The equation punishes round trips more severely than one-way missions. A one-way mission to Proxima must carry propellant to accelerate to interstellar speed. A round-trip mission must carry propellant to accelerate to interstellar speed, then propellant to decelerate at Proxima, then propellant to accelerate for the return trip, then propellant to decelerate back at Earth. Each of these 4 burns requires its own propellant mass. The propellant for the final burn must be carried through the previous 3. The propellant for the third burn must be carried through the previous 2. The rocket equation applies to each stage, compounding against the mission mass each time. A round trip requires, under the rocket equation, significantly more than twice the fuel of a one-way mission. The exact multiplier depends on the specific propellant and exhaust velocity, but it is always large, and it always makes the total required fuel mass at launch even more astronomical than the one-way figure. This is why every serious interstellar mission concept, when the mission architects are being honest about the physics, either accepts a one-way trip or accepts a flyby. A crewed round trip to Proxima with deceleration at each end is not just harder than a one-way trip. It is harder by a factor that, under chemical propulsion, pushes the required fuel mass past any conceivable supply on a different trajectory than the one-way case does. It is not merely twice as hard, it is several times harder, and the rocket equation compounds that factor against itself at each stage of the mission. The mathematics of a round-trip interstellar mission under chemical propulsion do not describe a hard engineering challenge. They describe a physical impossibility that no amount of engineering can address. Engineers and physicists have known about the chemical propulsion wall since the early days of the space age, which is why every serious interstellar proposal that followed tried to step outside chemistry entirely and into a different energy regime, one where the exhaust velocity is not limited by chemical reactions but by something far more powerful. The most physically developed of these ideas is nuclear pulse propulsion. The concept is straightforward in principle, even if the engineering is extraordinary. Instead of burning chemical fuel, you detonate nuclear bombs at the rear of a spacecraft in rapid succession. Each detonation produces a shockwave. A massive steel plate at the back of the ship, connected through shock absorbers to the main structure, absorbs each blast and converts it into forward thrust. The exhaust velocity of nuclear pulse propulsion is not limited by chemistry. It is limited by the products of nuclear fission, which carry far more energy per unit mass than any chemical reaction can approach. A project in the late 1950s and early 1960s called Project Orion developed this concept in serious mathematical and engineering detail. The physicists involved were not dreamers. They were people who had worked on nuclear weapons, who understood the physics deeply. Their calculations showed that a nuclear pulse ship could realistically reach somewhere between 1 and 3% of the speed of light. The engineering was brutal, but not impossible. The physics was sound. At 3% of the speed of light, the trip to Proxima Centauri takes roughly 140 years. 140 years. Compared to 73,000 years, this is a transformation. The number has moved from the scale of geological time to the scale of human history. A person born in the year the ship launched might have a great-grandchild alive when it arrives. The mission is not a geological event anymore, it is a multi-generational human event. But it is still longer than a human lifetime. A crew that launched at age 30 would arrive. if they could somehow survive 140 years in space at age 170. No human being has ever come close to that age. No life support system has ever been tested for that duration. No medical understanding covers what a human body does across 140 years in the radiation environment of deep space. The number moved. The problem did not. Fusion propulsion represents the next step up the energy ladder. Instead of fission, you fuse light elements together the way the sun does, releasing even more energy per unit of fuel mass. A fusion rocket, operating at theoretical peak efficiency, could potentially reach 10% of the speed of light. At 10% of light speed, the trip to Proxima takes roughly 42 years. A crew launched at age 30 would arrive at age 72, just barely within a plausible human lifespan, assuming perfect health, perfect life support, and no biological degradation from decades in deep space. There is one significant problem with fusion propulsion. It does not exist. Not as a rocket engine. Not even close. Humanity has not yet demonstrated sustained, controlled fusion in a stationary power plant that produces more energy than it consumes. Building a fusion drive capable of accelerating a crewed spacecraft to 10% of light speed is not an engineering challenge waiting for funding. It is a multi-generational research program with no guaranteed outcome. Above fusion, theoretically, sits antimatter. When matter and antimatter meet, they annihilate completely. Every gram of mass converts directly into energy with perfect efficiency, releasing more power per kilogram than any other known process. An antimatter rocket could, in principle, reach a significant fraction of the speed of light. In practice, the entire global supply of antimatter ever produced by human technology amounts to a fraction of a nanogram. Producing 1 gram of antimatter would require more energy than the entire world currently generates in a day. Storing antimatter without it touching ordinary matter and annihilating immediately remains an unsolved problem. The quantities required for an interstellar mission are so far beyond current production capacity that antimatter propulsion belongs in a different category from nuclear pulse, which was at least physically buildable. Antimatter propulsion is a physical possibility that the universe has arranged to be practically inaccessible. Here is the honest summary of where this leaves us. Nuclear pulse propulsion could have been built. It would take 140 years. That is longer than a human lifetime, and the crew would need to survive a radiation environment that no life support system has been designed for. Fusion propulsion does not exist and may not exist for generations. Antimatter propulsion requires resources the civilization does not have and may never be able to produce. Every step up the energy ladder narrows the gap. 42 years is closer than 73,000 years, but narrowing a gap is not the same as closing one, and the gap between 42 years and a survivable human mission remains its own version of the same wall the rocket equation created. The wall moved. It did not disappear. There is a pattern in all of this that is worth naming. Each proposed propulsion system is better than the previous one by a genuine and significant factor. Nuclear pulse propulsion is vastly more energetic per kilogram than chemical propulsion. Fusion is more energetic still. Antimatter is the theoretical maximum. And yet, with each step up, the trip time to Proxima at practical mission scales shrinks, but does not reach the threshold where human biology can plausibly survive the transit. This is not bad luck. It is the specific way that the interstellar distance problem interacts with the energy physics of propulsion. The distance to Proxima is large enough that even extraordinary improvements in propulsion reduce the required transit time from thousands of years to decades, but not to years or months. The biology problem requires years or months. The physics delivers decades. The gap between those two requirements is where every propulsion proposal has so far come to rest. It is also worth considering what these transit times mean in practical terms beyond the biology of the crew. A 42-year mission means launching scientists and engineers in the prime of their careers who will be in their 70s by the time they arrive, assuming perfect health. It means mission control on Earth cycling through multiple generations of personnel during the mission. It means the technology that launched the mission will be several generations obsolete by arrival. It means that the scientific questions motivating the mission will have evolved significantly during the transit, and the instruments designed to answer them may no longer be the instruments the arrival science requires. 42 years is not the same as 42 days. The organisational, technical, scientific and human costs of a 42-year mission are not simply a scaled version of a shorter mission. They are a qualitatively different kind of undertaking, one that no civilization has ever attempted and for which no planning framework currently exists. And this is before we have considered what actually happens to a spacecraft moving at 10% of the speed of light. Because at that speed, the environment of interstellar space changes in a way that most people have never thought about. There is a standard image people carry of interstellar space. Empty, cold, vast perfect vacuum stretching for trillions of kilometres in every direction, interrupted only by the occasional star. It is a reasonable image. Interstellar space is, by any everyday standard, about as close to nothing as anything gets. But it is not nothing. The interstellar medium, the material that fills the space between stars, contains matter. Mostly hydrogen. Roughly 1 atom per cubic centimetre on average, though this varies significantly by region. 1 atom per cubic centimetre sounds trivially sparse, and at low speeds it is. A spacecraft moving through this environment at the speeds of current missions would barely notice it. The collisions are so rare and so low energy that they contribute almost nothing to the mission profile. At 10% of the speed of light, the situation is different. At 30,000 kilometers per second, each hydrogen atom that strikes the forward face of the spacecraft is no longer a negligible particle in a sparse medium. It is a particle arriving at a relative velocity of 30,000 kilometers per second. The kinetic energy of a collision at that speed is not comparable to, say, a grain of sand hitting a windshield. It is comparable to the output of a particle accelerator. The kind of machine physicists build specifically to accelerate single particles to high energies and study what happens when they hit things. Your spacecraft is flying through a particle accelerator. The interstellar medium, at 10% of light speed, produces a radiation environment at the forward face of the ship that has nothing to do with cosmic rays or solar radiation. It is generated purely by the ship's own motion through a medium that is, by normal standards, almost empty. The faster you go, the more severe it becomes. The particle flux increases with velocity. The collision energy increases with velocity. At 20% of light speed, the numbers are worse. At 40%, they are worse still. The relationship is not gentle. What this means for a crew is concrete and unambiguous. Without shielding, the radiation dose from the interstellar medium at these speeds would be lethal within days. This is not an estimate with large error bars. The particle physics is well understood. The dose calculations are straightforward. The solution is shielding. Put enough mass in front of the spacecraft to absorb the incoming particles before they reach the crew. And here is where the interstellar medium trap closes. Shielding has mass. Adding mass to the spacecraft reintroduces the rocket equation. Every kilogram of shielding added to the bow of the ship is a kilogram that has to be accelerated to 10 or 20 or 40% of the speed of light. More shielding means more fuel to push the shielding. More fuel means more mass. More mass means more fuel. The rocket equation does not care that the mass is shielding rather than crew or cargo. It treats all mass identically. So the interstellar medium creates a trap with two jaws. Go fast enough to make the trip survivable for a human lifetime, and the radiation environment becomes lethal. Add shielding to survive the radiation environment, and the mass penalty reintroduces the propulsion problem you thought you had solved. The two walls grow together. The solution to one makes the other worse. There is one more aspect of this problem that is quietly specific to the speeds required for interstellar travel. Interstellar space is not purely hydrogen. It also contains dust. Microscopic particles of carbon and silicate, tiny by any normal standard, distributed sparsely throughout the medium. At low speeds, a dust particle is an irrelevance. At 20% of the speed of light, a dust particle the size of a grain of salt strikes the spacecraft with the energy of a small explosive charge, not metaphorically. The kinetic energy at those speeds is genuinely comparable. A larger grain, the size of a rice grain, would deliver an impact with the energy of a conventional bomb. You cannot navigate around individual dust grains. They are too small to detect at range, too numerous to avoid, and too fast approaching at relativistic speeds to respond to even if you could detect them. The ship must either absorb the impacts, which means more shielding mass, which means more fuel, which means the rocket equation again, or the ship must find a way to deflect or destroy incoming particles, which is an engineering problem of considerable difficulty that no current technology approaches. The universe has arranged the interstellar medium with the specific density that becomes problematic at exactly the speeds that would make interstellar travel biologically conceivable. This is not conspiracy. It is just physics operating on its own terms without any particular interest in what is convenient for creatures trying to cross it. Assume for a moment that the shielding problem has been solved. Assume that a propulsion system has been developed, somehow, that achieves a meaningful fraction of the speed of light. Say 20%. 60,000 kilometres per second. At that speed, the trip to Proxima takes roughly 22 years. A crew launched at 30 would arrive at 52. That is within a human lifetime. The physics of the trip, the shielding, the propellant, all of it assumed solved. At 20% of the speed of light, something else happens that the math requires. Time does not pass the same way for the crew as it does for the people who launched them. This is not a metaphor. It is not a philosophical observation about how time feels subjectively during a long trip. It is a measurable, confirmed, experimentally verified consequence of the structure of space-time, described by Albert Einstein's special theory of relativity and supported by over a century of precision experiments. The principle is called time dilation, and understanding it requires setting aside the intuition that time is a constant, that 1 second everywhere in the universe is the same 1 second. It is not. Time passes differently depending on how fast you are moving relative to something else. The faster you move, the slower your clock runs compared to a stationary observer. The effect is too small to notice at walking speed. At airplane speed, even at the speed of current spacecraft, the difference is measurable only with atomic clocks of extraordinary precision. But as velocity approaches the speed of light, the effect becomes dramatic. At 90% of light speed, the Lorentz factor, the mathematical measure of how much time slows, is approximately 2.3. Every 2 years on the spacecraft corresponds to about 4.7 years on Earth. At 99% of light speed, the factor jumps to roughly 7. The crew ages 1 year for every 7 that pass on Earth. At 20% of the speed of light, the effect is small but real. The crew ages slightly less than the Earth observers during the 22-year transit. Not dramatically less. The time dilation at 20% is modest, a Lorentz factor of about 1.02. The crew arrives about 4 months younger than they would have if time had passed uniformly. This seems like a minor detail. At 20% it is. But consider what happens if you push the velocity higher in pursuit of shorter trip times. At 90% of light speed, the trip to Proxima takes about 4.7 years in Earth time. For the crew, it takes roughly 2 years of personal experience time. A crew launched at 30 arrives psychologically and biologically at 32. The trip is survivable in terms of personal aging in a way it never was at slower speeds. But the Earth they return to is not the Earth they left. If the mission is a round trip, the crew spends 2 years going, some time at Proxima, 2 years returning, 4 years of personal time, perhaps on Earth depending on the precise speeds and durations. Something closer to 10 to 20 years have passed. The people who launched the crew have aged 10 to 20 years. Some of them may have died. The technology has changed. The political landscape has changed. The children the crew left behind are now adults. Time dilation does not give the crew more time. It takes time away from everyone else. The faster the crew travels, the more dramatically Earth moves on without them. At the highest relativistic speeds, a round trip to Proxima and back could see the crew return to a civilization a century older than the one they left. They would be, in every meaningful social and cultural sense, travellers from the past arriving in an unrecognisable future. This is not science fiction. This is the confirmed geometry of space-time. And there is still the question that relativistic speed raises, even setting aside the time problem. If you are travelling at 90% of the speed of light, and the interstellar medium contains even the sparse density of hydrogen and dust that the average region of the galaxy contains, the particle collision energy at that speed is not merely dangerous, it is catastrophic. The shielding problem at 90% of light speed makes the shielding problem at 20% look minor. The walls do not get smaller as you go faster, they get larger. The universe has constructed a set of interlocking constraints that respond to every increase in speed by making the other problems proportionally worse. The faster you go, the more radiation you absorb. The more radiation you absorb, the more shielding you need. The more shielding you carry, the more propellant you need. The more propellant you carry, the heavier the ship. The heavier the ship, the more propellant you need to push it. And all of this at speeds where time itself is bending away from you, carrying everyone you know into a future you will not recognise when you return. The civilizational disconnection that relativistic travel produces deserves more attention than it usually receives in discussions of interstellar travel. Consider a round trip. A crew departs for Proxima at 90% of the speed of light. From Earth, the one-way transit takes about 4.7 years. The crew experiences about 2 years. They spend some time at Proxima, then return. From the crew's perspective, the entire mission takes perhaps 6 or 8 years of personal time. They are biologically 6 to 8 years older than when they left. From Earth's perspective, the mission takes somewhere between 10 and 15 years, depending on how long they spent at the destination. The crew returns to Earth a decade after they left. That is not catastrophic, but the relationship between the crew and their civilization is not the same as it would be after a 10-year Antarctic expedition. The crew experienced 6 years. Earth experienced 10. every conversation between the crew and Earth during the mission was subject to light speed delay. The crew's subjective reality, the pace of their days, the aging of their bodies, operated on a different clock. Push the speeds higher to 99% of light speed, and the asymmetry becomes dramatic. A crew that leaves at 20 years old would return, by their own biological clock, at perhaps 28. Earth would have aged a century. Everyone they knew when they left is dead. The technology, the culture, the political structures, the language, all changed beyond recognition. They are biological time travelers, returned to a future that has no place for them, carrying the knowledge of a science that the civilization has had a century to surpass. Time dilation does not make interstellar travel more human. At the speeds where it makes the biological aging problem manageable, it makes the civilizational problem severe. At the speeds where the civilizational problem is manageable, the biological aging problem is severe. The universe has arranged these two constraints to cover each other's weaknesses from different directions. There is something in all of this that is not accidental. It is the specific way physical law operates at these scales, without favoritism, without exception, applying the same constraints to everything that tries to move through the universe at speeds the universe has decided are expensive. Even if the physics could be managed, even if some propulsion breakthrough appeared that solved the speed problem, and some shielding breakthrough appeared that solved the particle problem, and some relativistic navigation breakthrough appeared that solved the targeting problem, the mission still has to put a crew inside a vehicle for the duration of the transit. And the crew is biological. That is the constraint that every propulsion proposal eventually reaches. Not the fuel, not the radiation from the medium, the body. The specific, irreplaceable, non-upgradable biological architecture that constitutes a human being. Start with gravity. The human body evolved under the constant pressure of Earth's gravitational field, not as a background detail, as a structural requirement. Bone density is maintained by the mechanical loading that gravity imposes on the skeleton every day. Remove that loading, and the bones begin to resorb. Calcium leaves the matrix. The density drops. Astronauts on 6-month International Space Station missions return to Earth with measurable bone loss that requires months of rehabilitation. The longest single spaceflight on record is about 437 days, set by Valery Polyakov on the Mir space station. His recovery was long and difficult. A trip to Proxima at the fastest conceivable near-term propulsion speed, setting aside theoretical systems that do not exist, takes decades, not months. Decades. There is no confirmed data on what decades of low or zero gravity does to the human skeleton, because no human being has experienced it. The trend lines from the data that does exist are not encouraging. Bone loss in microgravity follows a trajectory that does not appear to stabilize at a new lower level. It continues. Whether it continues indefinitely or eventually reaches a new equilibrium is unknown, because nobody has stayed in space long enough to find out. The cardiovascular system follows a similar logic. The heart is a pump that works against gravity every minute of a terrestrial life, pushing blood from the legs up to the brain against a gravitational field. In the absence of gravity, the fluid distribution in the body shifts. The heart adapts to a lighter workload. It shrinks slightly. It becomes less capable of the job it was originally built for. Return a long-duration spaceflight crew to Earth's gravity, and the cardiovascular system has to perform a job it has partially forgotten how to do, suddenly and at full demand. Radiation is a separate thread running through all of this. galactic cosmic rays, high-energy particles born in the violent deaths of stars across the galaxy, stream through interstellar space in all directions. The Earth's magnetic field deflects most of them. The thick column of atmosphere absorbs most of what gets through. In deep space, beyond both of those shields, the dose is measurable and continuous. It accumulates in cells, causing DNA damage that the body's repair machinery handles imperfectly. Over months it adds up. Over years it adds up more. Over decades it becomes a significant biological cost that no life support system can offset, because there is no engineering solution to galactic cosmic rays at the shielding masses a crude spacecraft can practically carry. And then there is the mind. The psychological research on long-duration isolation is consistent across studies. 6 months in an Antarctic winter over station produces measurable cognitive changes in the third quarter of the mission. 12 months of simulation in a sealed Moscow habitat showed increasing withdrawal and dysfunction in the final stretch. The Mars 500 study, the longest isolation simulation ever conducted, found that extended confinement in a high-stakes confined environment consistently erodes the psychological systems that sustain high-performance decision-making. A trip to Proxima at the most optimistic near-term propulsion speed takes decades. The third quarter phenomenon would not be a bump in the mission. It would define most of it. The crew would spend the majority of the transit in the psychological territory that every isolation study identifies as the most difficult, not because they are poorly selected or inadequately trained. Because human beings evolved in groups, on a planet, with horizons and seasons and the presence of other people. They were not built for decades of confinement in a metal cylinder moving through featureless void. None of these biological problems are engineering problems. They cannot be resolved by better materials or more efficient systems. They are consequences of what biology is, a carbon-based organism built by natural selection for a specific planetary environment will not function indefinitely in the absence of that environment. This is not a limitation of current technology, it is a description of what life is. A crude interstellar mission, at any speed achievable under any currently developed or near-term propulsion concept, asks the human body to perform a function it is not built for, over a timescale it cannot survive intact, in an environment it was never designed to tolerate. There is a version of this problem that sounds manageable when stated simply. Astronauts on the International Space Station manage 6-month tours and return home with recoverable deconditioning, extend the mission duration, maintain the exercise protocols, and the body will adapt. The word adapt is doing significant work in that sentence, and it is doing it incorrectly. Adaptation implies reaching a new stable state. In low gravity, the body does not adapt in the sense of reaching a new stable equilibrium that maintains function. It degrades. The degradation may slow over time, but the trend lines from long-duration spaceflight data consistently show a direction: density decreasing, muscle mass decreasing, cardiac efficiency decreasing. These are not temporary states the body passes through on the way to a new normal. They are progressive losses. The longest single human spaceflight lasted about 437 days. The medical data from that mission, and from the cumulative data of all long-duration spaceflights, has been studied in detail. What the data does not contain is a demonstration that the body reaches a stable low-gravity state from which it can successfully return to Earth after several decades. That data point does not exist because no one has stayed long enough to generate it. A mission to Proxima at the fastest conceivable near-term propulsion speed, not the theoretical systems but the ones that could plausibly be built within this century, requires decades of transit. The body that would board that spacecraft and the body that would attempt to function at the destination are not the same body. One is the result of decades of living in a gravity well on a magnetically shielded planet. The other is the result of decades in a radiation environment with no magnetic field and gravity, provided only by a rotating habitat section. The radiation problem accumulates in a specific way that makes duration particularly damaging. The body's DINA repair mechanisms are effective but not perfect. Each repair has a small probability of being incorrect. Most incorrect repairs are inconsequential. Over a span of years, the accumulating background of incomplete repairs contributes to elevated cancer risk. Over a span of decades, the contribution becomes a near certainty rather than a statistical probability. And then there is the mind, which is a biological system as much as the bones are. The record for longest continuous human isolation in a simulated space environment is held by the Mars 500 study, 520 days. The data from that study showed measurable psychological deterioration across the crew in the final third of the mission. Not catastrophic failure. Measurable withdrawal, reduced initiative, disrupted sleep, declining social engagement. Those are the results of 520 days with the knowledge that Earth was right outside. A mission to Proxima takes decades. The third quarter phenomenon in a decade-long mission does not arrive at month 7. It arrives at year 6 or 7 and lasts for years. The social dynamics of a small group confined in a vehicle for years before arrival, with no meaningful communication from Earth due to light speed delay, with no possibility of return or rescue, and not the dynamics of a mission that existing psychological research has been able to model with any confidence. Human beings evolved in groups, on planets, with horizons and weather, and the presence of other people outside their immediate circle. They are not built for decades of confinement in a metal cylinder. This is not a limitation of current psychological screening. It is a description of what the species is. There is one proposal for interstellar travel that does not require solving the propulsion problem with nuclear or fusion technology. One proposal that does not require keeping a crew alive for decades. One proposal that is, in a genuine and serious sense, currently in development. It is called Breakthrough Starshot. The concept is this: make the spacecraft so small, so light, that the rules change entirely. Not a crewed vehicle. Not even an unmanned vehicle in the traditional sense of a bus-sized probe with cameras and instruments. A spacecraft the size of a postage stamp, a chip carrying a camera, a battery, a transmitter and a light sail, the whole assembly massing about 1 gram. Behind it, a ground-based laser array of extraordinary power fires a coherent beam at the sail. The photons from the laser strike the sail and push it forward. Photons have momentum. A small amount of momentum, but when you multiply small momentum by the output of a laser array generating hundreds of gigawatts of power and concentrate it on a sail of appropriate size relative to the spacecraft's mass, the acceleration is extraordinary. The Breakthrough Starshot concept proposes accelerating the gram-scale probes to 20% of the speed of light within a few minutes of the laser firing. 20% of the speed of light. 60,000 kilometers per second. At that speed, the trip to Proxima takes about 20 years. The probe arrives while the people who built it are still alive. It takes photographs, collects data, and transmits it back to Earth. The signal travels at light speed, taking 4.24 years to return. Roughly 24 years after launch, Earth receives images of the Proxima Centauri system, taken by a human-made device. The physics of this is real. The concept is not science fiction. The engineering challenges are enormous, including building a laser array of the required power, manufacturing chips that survive the acceleration and the transit environment. and designing a transmitter small enough to fit on a gram-scale spacecraft while still generating a signal detectable at 4.24 light-years. These are hard problems. They are not structurally impossible problems. Breakthrough Starshot, or something like it, will probably work. For a gram. Now add a human being. A human being with a minimally functional life support system, food for the trip, water recycling, air radiation shielding, a habitat, medical supplies, and the structural mass required to hold it all together. Masses somewhere in the range of several tons to tens of tons depending on mission duration. The laser acceleration that pushes a gram to 20% of light speed in minutes does not push several tons to 20% of light speed. The force from the laser is the same regardless of what you put in front of it. What changes is the mass it is pushing. A force that accelerates a gram to 60,000 kilometers per second accelerates a ton to 60 meters per second, which is about 216 kilometers per hour, which is roughly the cruising speed of a commercial airliner. The mass gap between a gram and a human crew is not a gap that engineering can bridge. It is a consequence of what light pressure is and what human beings weigh. To push several tons to 20% of the speed of light using a laser, the required laser power does not scale by the same factor as the mass. It scales worse. The numbers, when you work them out, require a laser array whose power output approaches what the entire sun produces in a reasonable fraction of a day. This is not an engineering challenge. This is a physical statement about the relationship between force and mass and velocity. Breakthrough Starshot demonstrates something genuinely important. It demonstrates that the distance to Proxima Centauri is crossable for a gram of information carrying hardware in a human lifetime. It is the proof that the stars are not unreachable. They are unreachable for biology, for mass, for people. For a gram of carefully engineered hardware carrying a camera and a transmitter, they are 20 years away. The line that Breakthrough Starshot draws is not between success and failure. It is between information and biology. Information can go. Biology cannot. Before closing the chapter on proposed solutions, two others deserve direct examination, not because they succeed, but because they represent the most persistent attempts to work around the physics rather than through it. The first is shortcuts through space-time. Einstein's equations of general relativity permit solutions that are deeply strange. Among them are traversable wormholes, tunnels through the fabric of space-time connecting two otherwise distant points. The mathematics is legitimate. The concept has been analysed seriously by physicists, most notably Kip Thorne, who in 1988 published a rigorous analysis of what a traversable wormhole would require. A spacecraft could, in principle, enter one mouth of such a structure, travel a short distance through the throat, and emerge from the other mouth light years away. What Thorne's analysis also established is what such a structure requires to exist. The throat of a traversable wormhole would collapse under its own gravity without something holding it open. The material required to hold it open must have negative energy density, a property that ordinary matter does not have. No naturally occurring substance with negative energy density has ever been detected. It may not exist. If it does exist, it exists in quantities so small and so difficult to access that building a planet-scale quantity of it, which is roughly what Thorne's calculations require, is not an engineering challenge. It is a question about whether the universe contains what the mathematics requires. The Alcubierre warp drive, proposed in 1994, presents the same fundamental issue from a different angle. The mathematics describes a bubble of compressed and expanded spacetime around a spacecraft, allowing the craft to effectively move faster than light relative to distant observers without locally exceeding light speed. The physics is exotic, but internally consistent. The problem is the exotic matter requirement, again in quantities comparable to the mass of a large planet, arranged in a configuration that is structurally unstable and requires continuous active maintenance. The math permits. The universe, so far, does not provide the ingredients. The second workaround is removing the people from the problem. Cryogenic suspension would freeze the crew at launch and thaw them at arrival. They would not age during the transit. The decades required for even a fast interstellar mission would pass with the crew unconscious, experiencing no time, arriving at the destination biologically fresh. The concept eliminates the biology problem, the psychology problem, the isolation problem, and the aging problem in a single solution. The biology of freezing human tissue has a specific and well-understood obstacle. Water inside cells forms ice crystals as temperature drops. Ice crystals are rigid, angular structures with sharp edges. Cell membranes are thin and fragile. The result of freezing living tissue without specialized cryoprotectants is widespread cell death from membrane rupture. Small organisms and isolated cell cultures can be cryopreserved with careful preparation. A human brain, with its 86 billion neurons and the precise structural connectivity that encodes every memory, skill, and aspect of personality, has not been preserved and successfully restored. The research continues. A solution is not guaranteed. Generation ships represent the other biological workaround. If the transit takes 400 years, send enough people that the population can sustain itself across generations. The people who arrive will be the great-great-grandchildren of the people who left. The mission continues. The destination is reached. Someone arrives. The problem with this framing is what it does to the word someone. The people who arrive did not choose the mission. They were born into it. They spent their lives inside a metal cylinder travelling through space because their ancestors made a decision before they existed. The mission that launched with a crew of volunteers arrives with a population that never volunteered. What obligation they have to the original mission, what relationship they have to Earth, what identity they carry as the descendants of a civilization they have never seen and that may have changed beyond recognition during the centuries of transit. These are not engineering problems. They are questions about what the mission actually is, and whether the thing that arrives is meaningfully connected to the thing that left. The shortcuts do not provide the ingredients. The biological workarounds either remain unsolved or redefine the mission until it is no longer clearly the mission that started. There is a problem that every interstellar proposal eventually reaches, one that is so obvious that it is sometimes overlooked entirely in the optimism of getting up to speed. Getting there is only half the problem. A spacecraft accelerated to 20% of the speed of light is still travelling at 20% of the speed of light when it reaches the Proxima Centauri system. It does not naturally slow down. Space offers no friction. There is nothing to push against. Whatever speed the ship was accelerated to is the speed it maintains indefinitely, unless something pushes back. Slowing down requires the same amount of energy as speeding up. This is not an approximation. It is a consequence of the symmetry of physics. To decelerate from 20% of light speed to orbital insertion speed requires providing the same delta V in the opposite direction that was required to achieve 20% of light speed in the first place. The rocket equation applies again, from the beginning, at the destination. There are only a few ways around this. One is to carry enough fuel at launch to both accelerate and decelerate. This doubles the propellant mass required which makes the rocket equation dramatically worse for the outbound leg, compounding the fuel mass penalty in both directions at once. One is to use some form of braking that does not require carried fuel. In principle, a sufficiently large and well-designed magnetic sail could interact with the stellar wind of Proxima Centauri as the spacecraft approached, using that interaction to slow down. This concept exists in theoretical form. No one has built or tested one. The engineering is extremely demanding, and the effectiveness at the relevant speeds is uncertain. One is to accept a flyby. Do not slow down. Race through the Proxima system at 20% of the speed of light. Take photographs and measurements during the hours or days when the ship is close enough to the target planets, and then continue into the void beyond, never stopping, never returning. For a breakthrough Starshot gram-scale probe, a flyby is the mission. There is no plan to stop. The probe fires through, captures data, transmits it back. The scientific return from a flyby at 20% of light speed is genuine and valuable. For a crewed mission, a flyby is not a mission. It is a tragedy. The crew travels for decades. They arrive at the destination. They have, at most, a few days in the system before they are past it and accelerating away into interstellar space beyond. They cannot stop. They cannot enter orbit. They cannot land. They cannot explore in any meaningful sense. They flash through the destination and disappear into the dark on the other side, travelling at 60,000 kilometres per second away from the place they spent decades trying to reach. If you want to stop, you pay twice. You carry the fuel for the outbound leg and the return leg, and the deceleration at the destination, and the mass of all that fuel must be accelerated on launch, and the rocket equation multiplies accordingly. The ship required to carry a crew to Proxima and stop there and return is not twice as large as the ship that just accelerates out. It is many times larger. And the larger it is, the more propellant it requires, and the rocket equation does what the rocket equation always does when you push it. The universe does not offer a free stop. Every kilometre per second you buy on the outbound leg is a debt that must be repaid at arrival, using energy you either carry from the beginning or somehow find at the destination. There is nothing at the destination. The physics of stopping is every bit as hard as the physics of going, and it receives a fraction of the attention. There is one theoretical approach to deceleration that does not require carried propellant. It is called a magnetic sail, or magsail, and the concept involves deploying a large loop of superconducting wire that generates a magnetic field around the spacecraft as it approaches the destination star. The stellar wind of the target star, a stream of charged particles flowing outward the way our sun's solar wind flows outward, would interact with this magnetic field. The interaction would push back against the spacecraft, slowing it. The physics is real. Stellar winds exist. Magnetic fields interact with charged particles. The concept is not physically impossible. The engineering, however, is extreme. At the speeds required for interstellar travel, the effective deceleration from a magnetic sail is modest relative to the problem. The superconducting loop would need to be enormous, potentially hundreds of kilometres in diameter, to generate a field large enough to create meaningful drag at interstellar approach velocities. Manufacturing, folding, deploying, and maintaining a superconducting structure of that size over decades of transit is an engineering challenge at a scale that makes the rest of the mission architecture look simple. And the effectiveness of the braking depends critically on the stellar wind properties of the destination star, which cannot be confirmed from Earth with current observation technology. Proxima Centauri is a red dwarf. Its stellar wind is not the same as our Sun's. Red dwarfs are known to produce intense flares and variable stellar wind conditions. Whether those conditions would cooperate with a magsail approach is uncertain. The honest assessment is that deceleration remains an unsolved problem for any crewed interstellar mission, and that the solutions proposed for it are all significantly harder than they initially appear. The universe charges full price for stopping, exactly as it charges full price for going, and there is no discount available at either end. This is worth holding in mind when evaluating optimistic interstellar mission proposals. The proposals that achieve impressive transit times to Proxima, the ones that get the number down to 20 years or 40 years, typically do so by assuming a specific propulsion system and focusing on the acceleration phase. The deceleration phase is often treated briefly, sometimes as a note that it requires equivalent energy to the acceleration, sometimes with a gesture toward a magsail concept, occasionally simply omitted. The omission matters because the deceleration phase is not a secondary problem, it is an equal problem that must be solved with equal resources. A mission architecture that can accelerate a crew to 20% of the speed of light has only solved half the mission. The other half, getting the crew to stop at the destination, and, if a return is planned, getting them back to Earth, requires the same physics solved twice more. Every time someone says that a proposed system could get us to Proxima in 20 years, the correct follow-up question is, and how do they stop? The answer to that question is almost always either they don't, or with the same energy all over again. The first answer produces a flyby. The second answer produces a mission that requires roughly 3 to 4 times the energy of the one-way acceleration phase. The universe bills in full, twice at minimum, and the second bill arrives when the ship is already light years from any supply. Everything discussed so far assumes that speed, shielding, biology and deceleration are the full list of problems. They are not. Underneath all of them runs a more fundamental constraint, one that does not care about propulsion type or crew health or mission architecture. It is energy. All of the proposed solutions to the interstellar travel problem require energy. Enormous energy. Energy at scales that are not comparable to anything current civilization produces. Consider the numbers. Total global human energy production in a year is approximately 580 exajoules. This is the sum of all electricity, heat, and mechanical energy produced by every power plant, every engine, every industrial process, and every fuel burned on Earth in a 12-month period. It is an extraordinary quantity, representing centuries of industrial development and the combined effort of 8 billion people and their machines. To accelerate a spacecraft of reasonable mass, say 1,000 kilograms of crew, habitat and life support, to 10% of the speed of light requires energy in the range of roughly 400 to 4,000 exajoules, depending on the propulsion system's efficiency and the specific mission parameters. Different assumptions about propulsion efficiency change the number significantly, but the order of magnitude is consistent across serious engineering analyses. In other words, a crewed interstellar mission, even at the lower end of the energy estimates, would consume somewhere between 1 and 10 times Earth's entire annual energy output, dedicated entirely to a single launch. Every power plant on the planet, running at full capacity, could be devoted for a year to producing the energy for one departure. This is before considering the deceleration at the destination, before considering the return trip, before considering the mass of the shielding, which is many times larger than the payload and must also be accelerated to the same speed. The full energy cost of a round-trip crewed mission to Proxima with deceleration and return is not 1 year of global energy production. It is closer to decades of global energy production for a single mission. Current civilization cannot do this, not because of political will or funding priorities or technological gaps that more engineering could close, because the physical infrastructure for producing that much energy does not exist, cannot be built on a single planet with finite resources, and cannot be grown quickly enough through normal civilizational development to be practically available on any near-term timescale. The physicist Nikolai Kardashev proposed a scale in 1964 for measuring civilizational energy use. A Type 1 civilization fully harnesses the energy of its home planet. A Type 2 civilization harnesses the energy of its home star. Current human civilization is estimated to be somewhere around Type 0.7, well below Type 1. The energy required for a crewed interstellar mission sits at the upper end of Type 1, at minimum. The gap between Type 0.7 and Type 1 is not a small engineering gap. It represents a transformation of civilization's relationship to energy that requires centuries of development under the most optimistic assumptions. And even a Type 1 civilization, harvesting every joule available from its home planet, would be committing a significant fraction of its total energy budget to a single mission. For a civilization to conduct interstellar travel routinely, the way we conduct transoceanic flight, would require Type 2 capability, the energy of a star. No civilization is known to have achieved this. The physics requires it. The engineering to reach it is many orders of magnitude beyond current capability. The energy wall does not respond to more engineering effort the way most engineering problems do. You cannot incrementally improve your way past it. You have to become a different kind of civilization. And there is no known path to doing that on any timescale that connects meaningfully to the people asking the question today. This is worth being specific about, because the Kardashev scale is sometimes presented as a roadmap, a sequence of steps that civilizations progress through with enough time and development. Type 1, then Type 2, then Type 3. And there is a seductive logic to this. Human energy production has increased substantially over the past 2 centuries. If it continues to increase, eventually it reaches Type 1, then continues to Type 2. The problem is the gap between Type 1 and Type 2. Type 1 means harnessing all the energy available from a home planet, including all incoming solar radiation, all geothermal energy, all chemical energy available from the planet's resources. It is an enormous step beyond where humanity currently is, but it is at least conceptually achievable within a planetary framework. Type 2 means harnessing the energy of the host star directly, not collecting sunlight from the planet's surface, where the atmosphere and the planet's curvature limit what is receivable. Collecting the star's energy from orbit, surrounding the star with collecting structures, capturing a significant fraction of what it radiates in all directions. The concept most associated with this is a Dyson sphere, or more realistically a Dyson swarm, a collection of solar collectors in orbit around the Sun at various distances. The mass required to build a Dyson swarm of meaningful coverage would have to come from somewhere. Calculations suggest it would require dismantling planetary bodies in the solar system to provide the raw materials. This is not an engineering project. It is the transformation of an entire solar system according to a design intention that must persist and be executed over centuries or millennia without interruption. No civilization is known to have done this. Astronomers have searched for the infrared signatures that a Dyson swarm would produce, a star that emits more heat than its light output would predict, because the collectors would re-radiate absorbed energy as heat. The searches have produced no confirmed detections. A civilization at Type 2 capability could attempt interstellar missions. A civilization below Type 2 cannot, at the energy scales the physics requires. and the distance between where humanity currently is and Type 2 is measured not in decades, but in transformations of civilizational scale that history gives no clear guidance on how to achieve. The walls covered so far in this script, the rocket equation, the interstellar medium, the relativistic effects, the biology, the shielding, the deceleration, the energy, are all fixed walls. They are properties of the physical situation that do not change with time. The distance to Proxima Centauri is 4.24 light-years today, and it was 4.24 light-years 100 years ago, and it will be approximately 4.24 light-years 100 years from now. Approximately. There is one more aspect of this problem that is quieter than the others, less dramatic than the rocket equation or time dilation, but present in a way that no interstellar mission can ignore. The target is moving. Every star in the galaxy is in motion. They orbit the galactic center, each on its own path, at its own speed. They interact gravitationally with neighbouring stars. They drift relative to each other over thousands and millions of years. The night sky looks fixed because the human timescale is too short to notice the motion. But the motion is real, continuous, and significant. Proxima Centauri is moving relative to our Sun at approximately 22 kilometres per second. This is not Proxima moving in some exotic sense. It is simply two stars in different orbits around the galaxy's centre, each following its own path, each arriving at different positions at different times. At Voyager's speed, the trip to Proxima takes 73,000 years. In 73,000 years, Proxima will have moved approximately 51 trillion kilometres from its current position. That is more than the current distance to Proxima. The star will be roughly twice as far from its current location as it currently is from us. A probe aimed at Proxima's current position would arrive to find empty space. At 20% of the speed of light, the trip takes 20 years. In 20 years, Proxima moves about 14 billion kilometres from its current position. That is roughly the distance from Earth to Neptune. The navigation correction required is not trivial. You must aim not at where the star is now, but at where it will be when the probe arrives, accounting for the precise relative velocities of both the Sun and Proxima in three-dimensional space, with no opportunity to course correct once the probe is at speed. The navigation problem is, in principle, solvable. The stellar motions can be measured and modelled to the precision required, but it adds another layer to an already extraordinary engineering challenge. And it is a quiet reminder that the universe is not holding still while you prepare. The destination is a moving point in four-dimensional space, not a fixed flag planted in the void. The motion of stars also means something larger. In 10,000 years, the nearest star to Earth may not be Proxima Centauri at all. The stellar neighbourhood is slowly rearranging. The star most accessible to our descendants, if they ever develop the capability, may be one that is currently dozens of light-years away, approaching on its orbital path. Interstellar navigation is not a problem you solve once and apply permanently. It is a calculation that must be remade for each mission, for each epoch, for each configuration of stars in a galaxy that never stops moving. The target is always moving. The universe never holds still for the shot. There is one more dimension to the motion problem that is rarely discussed. Our own Sun is moving. The Sun orbits the galactic centre at roughly 230 kilometres per second, completing one orbit every 225 million years. Over the 73,000-year transit time of a Voyager speed spacecraft aimed at Proxima, the Sun moves an enormous distance along its galactic orbit. The spacecraft, launched from Earth, inherits the Sun's velocity at the moment of launch. But as the years and decades and centuries pass, the gravitational relationship between the spacecraft and the Sun, and the spacecraft and Proxima, evolves in ways that make the original trajectory increasingly inaccurate. At breakthrough starshot speeds, 20% of light speed, the 20-year transit time means the Sun's motion during the trip is manageable. About 145 billion kilometres of solar displacement. Still a significant navigation correction, but one that can be calculated and accounted for. The deeper point is this. Interstellar navigation is not pointing a telescope at a star and drawing a straight line. It is solving a four-dimensional orbital mechanics problem in a medium with no fixed reference points, where both the origin and the destination are in continuous motion, where the medium between them exerts forces on the spacecraft throughout the transit, and where the only communication between the mission and its home civilization travels at light speed, meaning that any correction signal sent from Earth takes years to arrive and the response takes years to return. It is a problem solvable in principle. It is a problem that adds another layer of extraordinary engineering precision to a mission that is already operating at the outer edge of what physics permits at every other level of its design. The stars are not waiting. The galaxy does not hold still. Every calculation for every interstellar mission must be made for a specific departure date, a specific trajectory, a specific set of stellar positions, and recalculated from scratch for any other departure date. The sky that works for a mission in 2150 does not work for a mission in 2180. The stars will have moved. The geometry will have changed. The whole problem starts over. If you take everything this script has established and apply it not to humanity specifically, but to any civilization anywhere in the galaxy, a quiet conclusion begins to form. The rocket equation is not a human invention. It is a consequence of physics that applies to any civilization that achieves spaceflight on any planet around any star. The interstellar medium is not unique to the space around our Sun. It is the material that fills the galaxy. The biological constraints of carbon-based life are not specific to Earth organisms. They are consequences of what chemistry and physics do to structures that evolved on planets. Time dilation is a property of space-time, not of human technology. All of this means that every civilization in the galaxy, if any others exist, faces the same walls. The rocket equation blocked their early spacecraft the same way it blocked ours. The interstellar medium is as dangerous for their high-speed probes as it is for ours. Their biological crew members have bones and cells and minds that do not thrive indefinitely in deep space, for the same reasons ours do not. The Fermi paradox asks a question that has occupied scientists and philosophers for decades. If the galaxy is old and large and likely full of life, where is everyone? Why has no civilization made contact? Why is the universe silent? One answer that gets less attention than it deserves is the simplest one. The universe is silent because the distances between stars are genuinely, structurally, physics enforced hard to cross. Not for humanity specifically, for everyone. The walls in this script are not human walls, they are universal walls. Every civilization that has ever existed in this galaxy has looked up at the night sky and seen the same stars and run the same calculations and arrived at the same answer. The numbers do not cooperate, the energy is not available, the biology does not survive, the shortcuts do not exist. And so the galaxy is full of civilizations perhaps, each on their own planet, each looking up at stars they cannot reach, each listening with their own version of a radio telescope to a silence that is not evidence of absence, but evidence of physics. The silence of the universe may not be a mystery. It may be the expected outcome of a set of physical laws that apply to everyone equally. A universe where life is common, but contact is rare. Not because civilizations fail before they reach the stars, but because the stars are genuinely far enough away that reaching them is at the outer edge of what physics permits. There is something quietly important in this framing. The Fermi paradox is usually presented as a puzzle with a disturbing possible answer. Maybe civilizations destroy themselves before they can spread. Maybe there is a great filter, some catastrophic barrier that eliminates civilizations before they become interstellar. The possibility that the great filter might be behind us, something already survived, is presented as alarming because it implies we might be the first advanced civilization, which seems improbable given the age and size of the galaxy. But there is another version. The great filter might not be a catastrophe at all. It might simply be physics. The distances between stars, the energy required to cross them, the physics of high-speed travel through the interstellar medium. The biology of carbon-based life might collectively represent a filter that no civilization overcomes, not because civilizations fail, but because the filter is a property of the universe rather than a property of civilizations. If that is true, the universe is not a graveyard of failed civilizations. It is a collection of ongoing civilizations, each alive and developing on their own worlds, each looking up at the same unreachable stars, each building the equivalent of radio telescopes and sending signals into the dark, and waiting for an answer that the physics of the universe makes very difficult to deliver. The silence in that case is not ominous, it is expected. It is the sound of a universe where life exists, but the space between life is simply too large for biology to routinely cross. That interpretation does not reduce the strangeness of the situation. It is still strange to be alive on a planet surrounded by a galaxy full of stars that cannot be reached. But it changes what the strangeness means. It stops being a mystery about what is wrong with other civilizations and becomes an honest description of what the universe is. If that is the answer to the Fermi paradox, then the universe is not empty. It is full of life looking up at a sky it cannot cross, from planets it cannot leave, across distances that the universe has decided to make permanent. Before this script reaches its close, there is something that deserves to be said directly. The barriers described here apply to biology. They apply to mass. They apply to the carbon-based, water-dependent, gravity-requiring, radiation-sensitive structures that constitute human beings and any similar life form. They do not apply to information. A radio signal travels at the speed of light, not 20% of the speed of light, not 10%, the full speed, 300,000 kilometres per second. A signal leaving Earth tonight arrives at Proxima Centauri in 4.24 years. Not 73,000 years, not 42 years, 4 years, and 3 months. A signal carrying everything humanity has learned about mathematics, about physics, about chemistry, about biology, about music and language and history, travels that distance in the time it takes a child to go from first grade to 5th grade. This is not a consolation prize. It is not a lesser version of the real thing. It is the universe telling us, with considerable precision, what the currency of interstellar exchange is. Not bodies, not spacecraft. Information, the Voyager Golden Record, launched in 1977, contains sounds and images of Earth encoded on a physical disk. It is currently about 23 billion kilometres away, travelling at 17 kilometres per second. The same information, transmitted as a radio signal in 1977, would have already crossed the distance to Proxima Centauri 11 times by now. The physical object and the encoded information are not the same thing. The universe treats them according to entirely different rules. The information moves at light speed. The object moves at the speed a rocket could give it. Breakthrough Starshot, if it succeeds, will not send a person to Proxima. It will send a camera and a transmitter. A gram of hardware that carries the capacity to observe and report. The photographs it takes will travel back to Earth at light speed. The mission is not a physical presence at the destination. It is an extension of human perception across interstellar distance, using the only medium the universe charges at a reasonable rate. What we can send to the stars under known physics is everything we know. Every measurement, every equation, every piece of music, every image, every language, every question. We can send these things at 4 years delay. We can receive answers in 8 years. We can, in principle, conduct a conversation with a receiver at Proxima Centauri at roughly the pace of exchanging annual letters. This is not the same as being there. It is also not nothing. It is the universe's answer to the question of interstellar communication, offered at the maximum speed it permits, and if there is something near Proxima listening, the same physics applies to them. They can send us information at light speed. They cannot send us their bodies. They cannot arrive. What they can do is reach across 40 trillion kilometres in 4.24 years and make their presence known in the form of organised information that could not have been produced by chance. We have been listening for that signal for 60 years. The silence continues, but the physics of sending it is not in doubt. The asymmetry here is worth holding for a moment. A physical spacecraft aimed at Proxima Centauri under any propulsion system currently available takes decades to centuries to reach its destination. A radio signal aimed at Proxima Centauri arrives in 4.24 years. The same information, the same content, the same meaning, but the physical object and the electromagnetic signal are not the same thing in the universe's accounting. The universe charges them according to entirely different rates. This is not an arbitrary rule. It is a consequence of what mass is and what light is. Mass has inertia. Accelerating it costs energy. The more mass, the more energy. Light has no rest mass. It travels at the maximum speed the universe permits, with no energy cost beyond the cost of generating the photons in the first place. The Voyager Golden Record illustrates this with specific numbers. The record contains sounds, images, and mathematical information that together represent something of what Earth is. It took extraordinary engineering to place that record on a spacecraft and launch it into the solar system. And the spacecraft is currently 23 billion kilometres away, a distance that took nearly 50 years to cover at the fastest speed available chemical rockets could provide. The same information, encoded as a radio signal, could cross that distance in about 21 hours. If it were aimed at Proxima, it would arrive in 4.24 years. Not 50 years, not thousands of years, 4 years. What Breakthrough Starshot is attempting to prove is that even physical objects, if made small enough, can approach the transit times that electromagnetic signals achieve. Not the same transit time. That requires being massless, which nothing with structure can be, but close enough to cross the distance within a human lifetime. The mission succeeds for a gram because a gram is as close to massless as a structured physical object can be while still carrying instruments. The mission fails for people because people are not close to massless. They are, in the universe's accounting, expensive. There is an object leaving our solar system right now. It has been travelling since 1977. It carries a golden record containing sounds and images of a planet, greetings in 55 languages, music from Bach and Beethoven and Chuck Berry, the sound of rain and waves and wind, the brainwaves of a young woman in love. It was placed on that spacecraft not because the engineers expected it to arrive anywhere specific, but because they understood something important. The physical object would travel for tens of thousands of years and reach nothing in any timescale that mattered to the civilization that built it. But the meaning encoded on it travelled at the speed of light the moment it was described, the moment it was explained, the moment the story of what it contained crossed any radio transmitter on Earth and moved outward through space at 300,000 kilometres per second. Voyager is a message in two forms. The physical form moves at 17 kilometres per second and will never reach another star in any meaningful time frame. The informational form has already crossed the distance to Proxima Centauri 11 times. We will not make it to our nearest star. Not in the physical sense, not in the biological sense, not in the sense of a crew leaving Earth and arriving at Proxima in a spacecraft and setting foot on a world around another sun. The physics of that crossing is not merely difficult. It is a compounding stack of physical laws, each one independently severe, each one made worse by the solutions to the others, operating at a scale of distance and energy and time that no civilization running on a single planet has been shown to overcome. That is a true statement. It is worth saying honestly, without softening. But honest does not mean defeated. The nearest star is 24 light-years away. In light years, 4 years and 3 months. That is the universe telling you something specific. Not that the star is unreachable, that it is unreachable for biology, that the currency for crossing that distance is not mass or propellant or engineering ambition. It is information, organised and transmitted at the speed the universe permits. What you are doing right now, receiving organised information about the structure of the problem, is an act that operates at the speed of light. This script, or something carrying the same content, could be transmitted to a receiver at Proxima Centauri and arrive in 4.24 years. Every piece of knowledge about the universe that humanity has assembled, every equation and observation and hard-won understanding, travels at that speed. The stars are not unreachable. They are unreachable for the part of us that has a body. Look up tonight, if the sky is clear. Find Proxima if you know where it is, a faint red dwarf too dim to see with the naked eye but real, burning quietly with a fraction of the sun's energy, orbited by at least one planet that sits in the zone where liquid water is possible. It is 4.24 light-years away. It has been there for billions of years. It will be there for billions more. Every second, light from that star is arriving at Earth. Has been arriving all your life. Is arriving right now as you listen to this. That light left Proxima Centauri 4.24 years ago. It crossed 40 trillion kilometers of space. It passed through the interstellar medium, the same sparse gas and dust that would be lethal to a relativistic spacecraft, at the speed light moves through it, which is to say without hindrance. Light does not experience the interstellar medium the way mass does. It passes through. It arrived here. It arrives here every second, and somewhere on the other end of that beam, a star is burning, circled by a planet, surrounded by conditions we do not fully know, in a system that no human being has ever observed up close. The information about what is there travels toward Earth at the speed of light continuously, and has been doing so since the Sun formed and planets formed, and the geometry of the solar neighbourhood arranged itself into something close to what it is today. The distance is the same distance it has always been, 4,024 light-years. The physics is the same physics. The walls in this script, the rocket equation, the interstellar medium, the biology, the energy, none of them have changed. The universe did not soften any of its constraints during the course of this script. But the light is arriving. That is not nothing. In a universe that could have been structured so that no information crossed between stars at all, the fact that electromagnetic signals travel at the maximum speed physics permits, unimpeded, from one stellar system to another, is a gift of a kind. Not the gift that was asked for, not the physical presence, not the crew, not the flag, not the handshake with whatever might be circling that dim red star, but the gift of knowing, the gift of being able to look at a point in the sky and say, there is a star there, and it has planets, and its light reaches us, and we know enough about it to know what questions to ask. The distance is real. The barriers are real. The physics does not negotiate. But the light is also real. And it has been crossing the gap the whole time. Good night.